Hello, can you see my screen now?
Yes, sir.
Okay, so we'll try to do one or two more problems, then we'll move to other topics like regeneration, reheating, and intercooling. Okay, hello, hello.
Yes, sir.
Actually, someone voice is coming from the back. Who is this? Okay, now we'll start the class today. We'll do one or two more questions uh, of the questions which has been asked recently. We'll be doing that, and then we'll move to other topics. Okay, so we'll start. I'm giving you the data directly. This question was asked in actually GATE 2019. It was asked. So the question says that there are two turbines. I'm directly drawing the that. Okay, one, two, three, four. One, two, three, four. Okay, this is TS curve. Both are TS curves only. Okay, so it in the question they have mentioned that the isentropic efficiency of this first cycle uh, is zero point 0.7. Okay, and the pressure ratio RP is 3. For the second cycle isentropic efficiency we have to calculate, and the pressure ratio here they have given 5. Okay, gamma for the working fluid for both the cycle is same, that is air. Okay, so gamma is constant, that is 1.4. So we have to calculate isentropic efficiency of the second turbine. Okay, hello, hello.
Yes, sir.
Okay, so we have to do calculate the isentropic efficiency corresponding to the pressure that's RP, pressure ratio value of 5. Okay, so uh, I'll give you 3 to 4 minutes or 5 minutes. Try to do this. Otherwise, we will discuss this in this class. It is also based on all the formulas which we have uh, taken done in the class. So here I will give you a hint, because here the inlet conditions of the turbine are not given. So you can take CP value and temperature T3 as the inlet condition to the turbine. Here T3 condition, temperature you can assume T3. Okay, and now try to do it. It is a straightforward question, you can directly do. Oh, hello. There is one more hint actually in this question. In this question, they have said that actual work W actual of turbine one is equals to actual work done by turbine two. So both are equal. So you have to use this to calculate that isentropic efficiency. Now I think the question has become a bit more simpler. Hello, any one of you have got the answer? Hello, hello, am I audible?
Yes, sir.
So, any one of you have got the answer?
Doing so.
Okay, we'll do now. So, actually, what they have given in the question that the isentropic efficiency for turbine 1 is 0.17, and isentropic efficiency of this same turbine they have asked, but the pressure ratio has changed now. Previously it was 3, now it is 5. Okay, the actual work of turbine 1 and turbine 2 are given same, that is both are equal. Okay, so we'll use this in our question. This is an important term which they have given in in this question. So, so what is the isentropic efficiency of turbine? For turbine, it is a small upon big. We have asked. We know. So we can write H3 minus H4 dash upon H3 minus H4. Can we write like this?
Yes,
Hel-
sir.
Okay. So from here we know that this mm, this one is the actual work, and this is the ideal work. Okay, so what we can write, uh, S3 minus H4 dash is equals to eta of turbine into S3 minus H4. Okay, so this is we can directly write work actual of turbine is equals to eta of turbine uh, into Cp into T3 minus T4. Can we write like this? Now similarly we can write eta turbine into Cp. Now we can take out what we can take out, T3 can we take out, because initial condition is same for both, that is T3 they have mentioned it is same. So we can write T3 and 1 minus T4 upon T3. Can we write like this? Hello?
Yes, sir.
Okay, so now we already know that T2 upon T1 is equals to T3 upon T4 is equals to R to the power gamma minus 1 upon gamma. So can we put this entity here, eta T into Cp into T3 bracket 1 minus 1 upon Rp to the power gamma minus 1 upon gamma. Is it fine till now? Hello?
Yes, sir.
Now what we will get here? We can write work actual of turbine is equal to eta T into Cp into T3 1 minus 1 upon Rp to the power gamma minus 1 upon gamma. Okay, this is also closed. So what for turbine 1, what they have mentioned, turbine 1 which is running on Rp equals to 3 and initial condition Cp and T3 are same at the inlet of turbine for both turbine. So what we can write, W1 is equals to zero point 0.7, eta 1 is given 17 zero point 0.7 isentropic efficiency, so zero point 0.7 into Cp into T3 1 minus Rp equal to 3, gamma they have given 1.4, so 1.4 minus 1 upon 1.4, this closes, this whole we can get, so it will become 1. Similarly for turbine 2 we can write, it is Rp equals to 5, Cp and T3 are same inlet conditions. Okay, and here gamma we have to calculate, so what we can write, omega 2 actual work done by turbine 2 is equal to eta 2 into Cp into T3 1 minus 1 upon 5 to the power 1.4 minus 1 upon 1.4. Okay, now what it is given, actual work done by turbine 1 and turbine 2 is given same, so we can equate this equation 1 and then equation 2 directly. So what we will get here, can you calculate and tell me what you have got, because CpT3 will cancel out and only or the value which we want to calculate eta 2 will be the remaining term, so we can easily calculate out it here.
Excuse me, sir.
Yeah.
Sir, can you kindly show the question because I just joined a few minutes.
Okay. Will I wait? I'll first finish that. It is because about to finish. Then I'll show you.
Sure, sir.
So eta 2 into Cp into T3 1 minus 1 upon 5 1.4 minus 1 upon 1.4. Okay. So here Cp T3 will cancel out. Only eta 2 is remaining. So we can calculate what you have got eta 2. Can you calculate and tell me? This is the question. Actually they have written this question came for actually that uh, uh, mm, filling the blanks type of question, in which you have to fill the value.
So this was the first question for the day?
Yeah, this was the first question which we are discussing today.
Okay, sir. Thank you, sir.
Can anyone tell what is the value of isentropic efficiency of turbine 2 which you have got?
Is it
Is it
0.52?
0.5? Yeah, it is right. Actually they have in the get question answer key, they have given the value between 0.50 to 0.52. So if you will fill any value between these two, your answer will be correct. Okay, so they generally give a range uh, in the exam. The question came for filling the blanks type of question, and they have asked to write the value up to second decimal value. So 0.52 is the correct. Has everyone got it? How we have proceeded in this question? Hello?
yes, sir.
Okay. Now another question came in actually. It is a simple question, straightforward. We have done so many questions like this in the class. The question is that this question came in GATE 2017. Okay. So what they have given the that air is the air is entering the uh, air is entering the gas turbine. Whose value of Cp is given 1040 joule per kg Kelvin, and gamma equals to 1.4. Okay, so the pressure ratio also they have given Rp is equals to 10. Inlet temperature to the turbine they have given, that is T3 they have given 1200 Kelvin, and isentropic efficiency of the turbine they have given 0.9. So they have asked to calculate the temperature T4 dash. Wait, I'll draw that cycle. Can you calculate that? 1, 2, 3, 4, 4 dash. So they have asked to calculate T4 dash. This was also for 2 marks. Previous question was also for 2 marks they asked. This was also filling the blanks type of questions. And they asked the value of the temperature T4 dash in Kelvin.
Is it 679 Kelvin?
Yeah, it is right. Should I discuss this question, or you can do it by your own? Okay, I'll discuss quickly. So what we have to call it T4 dash. Okay, so direct this is a TS curve actually, temperature entropy curve. So isentropic efficiency of turbine is given by directly I will write that in terms of temperature T3 minus T4 dash upon T3 minus T4. Okay, so from from here T3 we know, so T3 upon T4 is equals to Rp to the power gamma minus 1 upon gamma we know, so T3 is 1200, T4 we can calculate 10 to the power 1.4 minus 1 upon 1.4. So from here we can calculate T4, and then we can put this value of T4 here. So everything here is mentioned. So eta T is equals to T3 minus T4 dash, T3 minus T4. So 0.9 T3 minus 1200 minus T4 dash upon 1200. What is the value of T4 you have got? Hello?
622 Kelvin.
622 Kelvin. So we will put here 622 Kelvin. So from here we can get T4 dash, what it is, 679 Kelvin. Okay. Now we'll move to another topic, because these all this type of questions only, level of questions only they will ask in the gate exam, because time is limited. They will you cannot they cannot give a very tough question also, because you have to solve 65 questions in roughly 3 hours. So if you give uh, more than 5 or 10 minutes for one question, so they designed the question in such a way that more than 40 to 50 per questions you can easily solve. Now we'll move to another topic, that is uh, regeneration regeneration in gas turbine. Okay, Now this topic is basically related to uh, how to improve performance of a gas turbine. So basically there are three ways by which we can improve the performance of a gas turbine. First, by regeneration.
Sir, it is not visible, sir.
What my screen is not visible.
Yes, sir. Yes, sir. Got it.
Now it is visible, sir.
Now it is.
Okay, so first one is the regeneration in gas turbine. Second is reheating. Okay, and third one is intercooling. Okay, by these three steps we can improve the performance of the existing gas turbine. Okay, so we'll discuss one by one, and then we'll solve one big problem, like a conventional type of problem, from which you can get the all three processes in the same problem. Okay, so first we will start discussing with regeneration. Okay, so what is regeneration? Regeneration in gas turbine is basically a process in which turbine exhaust gases which are coming out of the turbine, they are actually heated up. So we are utilizing those gas to increase the temperature of the compressed air coming from the compressor. So basically what will happen? It will decrease the heat addition which is required in the combustion chamber. Okay, so what I'll write that here. Regeneration is a process in which turbine exhaust gases are utilized to, I am making increase sign like this, increase the temperature of compressed air before entering combustion chamber. Okay, so wait, I'll show you in this from a diagram. This is the compressor. Okay, so from compressor what actually happens, the uh, compressed air goes to combustion chamber. From combustion chamber they go to turbine. Okay, so this is the one, this is the step 2, this is step 3, this is step 4. So what we are using, we are using these exhaust gases here, okay, to increase the temperature of the, this is a regenerator. Okay, okay, so what we are okay, so this is T4 only. So we are actually what we are using, this T4 temperature will decrease because it will supply heat. So TV after exit it will become TV, here 2 will be there. So after from the regenerator temperature will increase and it will become A. Okay, so we'll draw that in TS diagram. TS, this is a TS diagram. So 1, 2, 3, 4. Turbine exhaust gases are used to increase the temperature. So the temperature here will drop to TB. Okay, and here temperature will increase because gases, we are utilizing the gases to increase the temperature. So here temperature will become TA. Okay, so can anyone tell what will be its effect? Wait, this is the regenerator, and from here to here it is combustion chamber. Okay, hello. So can any one of you tell me with what will be the difference uh, in each and every process, like compressor work, turbine work, heat addition, heat rejection efficiency, network output uh, uh, of the process? First, I will tell you, then you try to answer in the other process like reheating. Okay. First, so because suppose wait, I will draw two diagram first. One, two, three, four. One, two, three, four. TV, TA. Okay. So here it will be regenerator. I'm just writing out. Here it is combustion chamber. Okay. So what will be the effect? Suppose this is a idle Brayton cycle 1 2 3 4, and it is a regenerative heating cycle. So what will be the effect on the compressor work? Uh, will it increase or decrease, or it will remain constant?
Remain constant.
Yeah, right. Second, turbine work. What it will have effect on turbine work?
It will decrease.
No, it will also remain same, because turbine work is this one, na? It will remain same. What is turbine work? S3 minus H4. So S3 minus H4 is both the in both the cases is same, na? So it will also remain constant. The third is heat addition. What will be the effect on the heat addition? QS. Q supplied means heat addition in this cycle, in this cycle.
It will be less
Yeah,
for regenerator.
yeah. For this cycle, it will be H3 minus H2, and for this regenerative heat cycle, QS dash, what it will be? H3 minus HA. So it will decrease. So this type of question only they try to ask in that one marks question. They will give a question in a regenerative heating cycle. What will be the effect on the heat addition? Increase, decrease, remain constant? None of these. Like this type of question they only ask for 1 marks. So another is network output. What will be the effect on the network output? Network output is turbine work minus compressor work.
No effect.
Yeah, it will remain constant. Now efficiency. What will be the effect on the efficiency?
Will increase
Yeah, it will increase. Why it will increase?
because heat input is less now.
Yeah, you can write like this. You are upon QS. So since QS is low, okay.
Sir,
Hello. Yes.
sir, actually the heat rejected is also decreasing, sir. So
Yeah,
won't it affect?
that I will talk about. So because we can write directly, network is constant, heat rejection is decreasing, so efficiency will improve. Now heat rejection, QR, heat rejection will also will decrease. Previously it was S4 minus H1. Now what it is? HB minus H1. So it will decrease. Now what will be the effect on mean temperature of heat addition? Basically, the mean temperature of heat addition is the temperature mean temperature between the process. Okay, suppose in cycle 1 heat is added between uh, 2 to 3. So what will be the mean temperature of heat addition here? T2 plus T3 divided by 2. So what will be the effect on the mean temperature of heat addition in case of regeneration cycle?
Will increase.
Yeah, it will increase. Why? Because temperature Ta is greater than T2. So T3 plus Ta divided by 2. So it will increase. And mean temperature of heat rejection?
Decrease, sir.
Mean temperature of heat rejection? Yes, it will decrease. Previously it was T1 plus T4 divided by 2. Now what it will be? TB plus T1 by 2. So it will decrease. And what will be the effect on the specific fuel capacity? Specific fuel capacity is basically the amount of fuel required to supply the heat. So what?
Remain same, sir.
No, it will decrease.
Increase.
Why? Because here in this cycle we are supplying heat from 2 to 3. Now we are supplying from Ta to T3. So less fuel will be required, na? Therefore it will decrease. Is it okay? Hello?
Okay, sir.
Okay. Now we will go. We will.
Sir, but actually the formula is something divided by work done, net work done.
Yeah,
So I
but
thought like since it is same.
no. Here from this we can directly see now. Here heat addition, heat supplied is less, reduced. So if heat supplied is reduced, then how can the fuel will be remain constant? Same fuel will be required.
Yes, sir, yes.
Now we will determine the effectiveness of the regenerator. Okay. So it is given by formula epsilon naught. Okay. So it is also called or thermal ratio or degree of regeneration. So they can ask in any form. They can ask what is the effectiveness of regenerator or thermal ratio of regenerator or degree of regeneration. So anything they can ask.
Excuse me, sir.
Yeah.
Uh, Here in efficiency formula on
Hmm.
left side, 1 minus QR upon
Yeah.
QS.
Yeah.
So QR decreases and QS also decreases, na?
Yeah.
And but net effect of QS is dominating, sir.
Yeah, QS is dominating. That's why our efficiency is improving.
Okay, sir.
Sir, how is it related to the mean temperature of heat addition?
Mean temperature of heat addition, it is basically the temperature. Just it is a term to explain the temperature ratio. Mean what is the mean temperature during heat addition of the air which we are supplying to the on which we are supplying the heat. Okay, so it is just a terminology we are using. So in because the ES exam they generally asks. That's why I have giving you this also, because they can also ask this question in gate exam also for 1 marks. That's why I have tried to.
Yes, sir, yes.
It is just a terminology. It is the mean temperature at which heat is being supplied, or you can say that average temperature.
Got it.
So what will be the efficiency of the regenerator? So here in the from here we can. So what will be the effective? You tell. Hello. What will be the effectiveness from this diagram? You tell. I'll write here. mean first wait. First I should write the definition. Wait. So it is defined as the actual temperature rise and regenerator, okay, to the maximum possible temperature rise in regenerator. So what will be the actual temperature right in the regenerator? Tell me from this.
TA minus T2.
Yeah, it is right. It is Ta minus T2 upon maximum possible. What is the maximum possible temperature rise which we can get?
T4 minus T2.
Yeah, it is right. T4 is the maximum temperature and T2 is the minimum temperature. So the difference which we are getting, it is the maximum temperature rise which we can obtain, but we are only obtaining Ta minus T2. Rest it is lost. Okay. So basically the efficiency effectiveness of the regenerator is 0.7 to 0.8 only, or you can say that it is only 70 to 80% effective. There is will always be a loss of 20 to 30%. But in ideal regenerator, what we want for ideal regenerator, effectiveness to be 1 or 100%. Okay. So for wait here first I should write that effectiveness is equals to Ta minus T2 upon T4 minus T2. Okay. So for ideal regenerator, we want effectiveness should be 100% or 1. Okay. So what we will get, if we will put the epsilon value of 1 here, Ta minus T2 upon T4 minus T2. So T4 minus T2 is equals to Ta minus T2. So from here what we can get, T4 is equals to Ta. So it is a very important term for ideal regenerative cycle. Okay. So for ideal regenerative regenerator or regenerative cycle, to happen, epsilon should be 1, T4 should be equals to Ta. Okay. This T4 which we are talking about here, T4 should be equals to Ta. Okay. And another term, what should be equal? Tb equals to T2. These three are important. Okay. Hello.
Yes, sir.
Yes.
Okay. Now we will. Should I write the derive the formula for efficiency, or should I tell you the formula directly? What do you want? Now we will calculate the efficiency of the ideal regenerative cycle. Okay. So what we know, that efficiency is equals to net work upon heat supplied. Okay. Or we can write 1 minus heat rejected upon heat supplied. This also we can write. Hello.
Yes, sir.
Okay. So for a Brayton cycle, what is the efficiency we can write? Tell me from this diagram. Wait, I'll draw a diagram here only because it will become confusing. 1, 2, 3, 4. So what will be the that heat rejected? It will be H4 minus H1 upon H3 minus H2. Is it okay? Similarly, we can what we can write 1 minus we can write directly in terms of temperature T1 T3 minus T2 CP will cancel out. Is it okay?
Yes, sir.
Okay. Now for regenerative cycle, for ideal regenerative cycle, epsilon should be 1 and Ta should be equals to T4 and Tb is equals to T2. So can we substitute Tb in terms instead of T2 and T4 instead of T4? Can we wait. This is for what we have written. This is for Brayton cycle. Okay. For regenerative cycle, it will be different. What it will be? Efficiency for regenerative cycle will be 1 minus. Here heat addition and rejection will change. Na?
TB minus
Yeah,
T1.
1 minus 2, 3, 4. So what do you want? This two should be same. So it will be, what was this point? TB or TA? It
Now
was
it was TB.
it was B, it was A. Okay. So what will be the efficiency of a regenerative cycle? 1 minus heat rejection. What was this? TB minus T1. Okay. Divided by T3 minus TA. Is it okay? Hello? I have
Yes, sir.
written directly because the H it will be HB minus H1. So CP will cancel out. So I have directly written in terms of that only temperature terms only. Okay. Now for ideal regenerative cycle, epsilon should be 1 and Ta should be equals to T4 and Tb is equals to T2. Okay. So we will put these values here. Instead of Tb, we will write T2. Instead of Ta, we will write T4. Okay. So what it will become? 1 minus T2 minus T1 divided by T3 minus T4. Okay. Hello.
Yes, sir.
Can we write this as like this? From here we can take out T1. So it will become T2 minus T1 minus 1. And from here we can take out T3 and 1 minus T4 upon T3. Okay. Now similarly here what it will become for ideal regenerative cycle, it will become 1 minus T1 upon T3. Okay. So T2 upon T1 minus 1 upon 1 minus T4 upon T3. So T2 upon T1 is equals to T3 upon T4 is equals to Rp to the power gamma minus 1 upon gamma. So eta ideal regenerative cycle, it will become 1 minus T1 upon T3. Okay. Upon Rp to the power gamma minus 1 upon gamma minus 1 upon 1 minus Rp to the power gamma minus 1 upon 1 upon Rp to the power gamma minus 1 upon gamma. Is it fine?
Yes, sir.
Now this we will cross multiply here, so it will become 1 minus T1 upon T3. So Rp gamma minus 1 upon gamma minus 1 upon Rp to the power gamma minus 1 upon gamma minus 1 upon Rp to the power gamma minus 1 upon gamma. Okay. So this upper terms will cancel out each other. So what will it will remain? Ideal regenerative cycle. It will remain 1 minus T1 upon T3 into Rp to the power gamma minus 1 upon gamma. This will come upwards. Okay. So this will be the efficiency for the ideal regenerative cycle, where T1 is the minimum temperature and T3 is the maximum temperature. So we can also write this as ideal regenerative cycle 1 minus T minimum upon T max to the power Rp to the power gamma minus 1 upon gamma. Okay. Hello.
Yes, sir.
Hello, sir.
Yeah.
Sir, in the previous session, in one question, you said this efficiency is equal to work ratio.
Where?
In previous session, in one question.
Okay, that we will discuss in the last. Right now, we'll discuss this on this part. Once this will be over, at the end of the class, I'll answer your that doubt. Okay.
Okay.
Please remind me at the end of the class.
Okay.
Okay. So, is it okay for you till this?
Yes, sir.
Okay. So, based on this only, we'll solve one problem that was asked in the GATE exam.
Sir, previous slides.
Okay, you can see.
Okay, sir.
Okay. Should I give one question to you, which was asked in the GATE based on this only, which we have discussed today? Hello?
Yes, sir.
Okay. I'll give you. So the question was asked in GATE.
Excuse me, sir.
Yeah.
Sir, in the previous class actually, can you tell what topic was done?
What was that?
Topics, previous class topic.
Actually, we are going in continuation. Actually, I have given when I have given that to NPTL in the NPTL to the NPTL madam. Actually, I have given that I will be teaching first gas turbine basics, the second regeneration, reheating, and all those, and at last I will be discussing all the question. But I thought that after completing each topic, I should discuss the question. That it will become more easy for you to understand. That's why I am discussing question along with the topics.
Okay, so sir, previous class recording, can you?
Actually, I have shared you my channel. Wait, I'll share you my channel again. First,
Okay, sir, you can complete it at the end of the class.
okay. I'll share my that channel. You can follow.
Sure, sir.
Uh, you can get that class from there. Also, I will share the link of the first two lectures also.
I have shared the channel links, sir.
Okay, okay. Thank you. So I'll give you one question. This was asked in GATE 2016. It was also a filling the blanks type of question. Okay. So what they have asked that in a simple Brayton cycle mm, with perfect regeneration. Perfect regeneration means ideal regeneration. Okay. Brayton cycle with ideal or perfect regeneration. Okay. Pressure ratio they have given Rp is equals to 6 and the value of the gamma they have given 1.4. The ratio of the T minimum to T max they have given what they have given 0.3. Okay, so they have asked the ratio of the thermal efficiency of a Brayton cycle to the ideal regeneration cycle. They have asked this. So can you calculate?
0.3 only.
Hello? Hello?
Yes, sir.
1 by 0.3 only, sir.
1 by 0.3? Yeah, it is 0.3. 1 by 0.3, not 0.3.
Yes.
So can you do this question? I'll give you 2 or 3 minutes.
So 3.33.
No, it is not right. I'll give you the formula also. For Brayton cycle, what it is? 1 minus 1 upon RP to the power gamma is.
minus 1 by lambda.
Yeah. For idle regenerative cycle, I have mentioned T
Minimum by
minimum upon T max,
maximum.
RP to the power gamma is 1 upon gamma. So you have to take this ratio only. Just there was this only.
At 0.8,
Yeah, point 0.8 more values 0.812 what.
0.802.
Yeah, it is correct. They will give a range from point 0.8 to 0.80 to 0.82. They have given this range, so your answer is correct. So we'll try to solve this. 1 upon RP they have given pressure ratio 6. Okay, so 1.4 minus 1 upon 1.4 divided by 1 minus, they have given the ratio T minimum upon T max 0.3 into 6, 1.4 minus 1 upon 1.4. Just you have to put the values and you will get the answer. It is 0.814. Actually, the answer it is. Please calculate and give. Hello.
Yes, sir. 0.8 is coming.
Okay. But I'll give 1 or 2 more questions. People have this cycle. Let's see. Only this question they have asked, I think, for this.
Sir, I am getting 0.802, sir.
Yeah, it is fine. I have given you the range. Na? They'll always give a range in the GATE exam. If they
Okay,
are
sir.
0.8 to 0.82, any value between this is correct. So have you got this? Only the formulas are important. Derivation they will won't ask. Like this formula, it is important. They will ask question directly on this. If you know this formula, you can easily answer like the one we have solved. They'll ask this type of values. These four, and they can give you in that four question and give four option and ask you for idle regenerative cycle T4 should be equal to TA. The abbreviation can change. The effectiveness should be 1, TV equals to none of these, all these type of, or they can ask all of these. Also, these are important. So these only these things you have to remember, and this hold, because they can ask question on this directly. So only 2 or 3 things has to be remembered. Rest derivation is there is no need to for you to remember the derivation part. Just remember the formula, and you will put the values, and you will get the answer directly in the exam. Hello.
Okay, sir.
Okay. Now we will move to another topic, that is reheating. Hello.
Yes, sir.
Okay.
Sir,
Yeah,
I think another class has started, sir.
it has started. But I think today there is no other class now.
No, on a Saturday's link there is class.
Okay, okay. Okay, then we will stop. We will discuss this in other class. It will only require, I think, one more class to finish this gas turbine, and then we can start directly steam power plant, that is Rankine cycle based. Okay, so these two topics are very important. Rest another topic. If there will be time, then we'll discuss. Hello.
Yes, sir.
Okay, sir.
Okay. So one person who was that who was having doubt.
Hello, sir.
Yeah. Hello.
Yes, sir.
Wait. Can you wait for some time? Rest and everyone can leave. The class is over.
Thank you, sir.
Okay.
Okay,
Thank you.
thank you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you. Hello.
Yes, sir.
Yeah. Now you can ask what is the problem you were
Sir,
facing.
you said work ratio equal to 1 minus T1 by T3 into RQ power gamma minus 1 by gamma.
Which topic you are talking about? Can you?
In one question, I can't remember.
Were we discussing the numerical part?
Yes, sir. Numerical part.
Which topic you were topping in this question?
In which in Brayton cycle you explain about work ratio,
Work ratio.
back work ratio and work ratio.
Okay. So this one.
Yes, sir.
So what is the problem you are facing here?
In this, you said after this one question in you said by one way RW equal to 1 minus T1 by T3 into RB per common son by gamma, and by this we solve another question.
Okay. Wait. I think the question I have that. Was this question
Uh,
1 upon 2.5? This question you are talking about?
yes, sir. Yes, sir.
So what is the problem you are facing in this problem?
RW. I doubt, sir, how RW equal to this T1 by T3 into RP per gamma minus 1 by gamma.
This one, T2
Yes, sir.
upon. So it is
No,
it
no.
is it is directly we know the for isentropic process, na
Yes. Okay,
isentropic.
sir. I will find the question, then I will ask you.
No, you can tell if you are you can just tell me the question. I'll write and then I'll clear it out.
Sir, I only remember that and don't remember question. So then I will find and I will come to you.
Okay. Was that a numerical problem?
Yes, sir. Remember, sir.
I think the backward ratio problem I have discussed only one or two problem. Na?
Yes,
This
sir.
was the
In
one.
one problem you solve another way, but you say by this we also solve it.
Okay. Actually, I
Just a
don't.
hint you say.
Yeah, this only I said in this problem only. I said turbine work was given na 2.5 tons of compressor work. So I
Yes,
said
sir.
that
Yes.
here we can turbine work, compressor work upon turbine work. Uh, we can get it. Compression upon turbine work is back work ratio. So from here we can also solve. I said that by putting that formula. Uh, but you can directly put the values here also, na turbine work and compressor work, and from here you can get the values.
Yes, sir. Yes. Okay.
There are two methods I said. Either to put value directly in the
Yes, sir.
turbine
Yes,
in
sir.
this
Yeah, yeah,
compressor,
yeah.
or
Yes.
you can calculate, because sometimes they can ask now what will be the back work ratio if the turbine work and compressor is 2.5 times of the compressor work. So they can
Yes.
ask in 1 mark question in the exam that
Yes.
what will be the back work ratio, or they can ask what will be the work ratio. So 1 minus back work ratio we can calculate will be the work ratio. So many questions can arise.
Okay.
If you'll remember the basic these 7 formulas, you can solve each and every questions of the gas turbine.
Okay.
Just
Thank you, sir.
you need not to remember derivation and all those things. Just thoroughly revise the that formula. Remember this formula and the TS diagrams. Rest you can do
Okay.
each and every question.
Okay.
Is it okay?
Yes.
Okay. Okay.
Okay, sir. Thank you.
Okay. Bye.
Bye.